What are the components of a solar electric system? In this lesson, we're going to start to go through the different major components that we use to create different solar electric systems. Now, as everything we do, the application and the system type and the specific equipment that we choose is going to determine what are all the different components that we need. And so we're going to start to understand more of the products available, the terminology that we're going to see out there in the market, and understand how these things a little bit go together to create an overall functioning and safe electrical system. Now, if we look at this residential solar system, we're kind of looking and highlighting some of the major components here. Of course, we understand that we're going to have a PV array. PV array is going to generate our DC electricity from the sunshine, and then we're going to take that DC electricity, and if we want to use an AC systems, which most of the time we do unless it's very small applications, then we're going to use a device called an inverter. And an inverter takes DC electricity and turns it into AC electricity so we can use common AC electrical devices in our home or in our business or whatever our application happens to be. So an inverter is going to be a conversion device. It makes the solar energy usable so we can connect it and have it act like normal electricity that we would have in our house already. If we have or need storage, storage usually means a battery system, some type of battery technology that we can use to store energy. If we need it, we don't always need to store energy, but if we're using energy storage, that's going to be another major component in the system. And then, of course, things like disconnects, so we can isolate and turn on and off, operate electrical systems, and meters are things that we can use to measure energy production or energy consumption. So these are some of the basic components that are going to go into a solar system depending on the type of setup that we're trying to design. So let's start by looking at PV modules in a little bit more detail. So the PV array is usually multiple modules put together in some electrical configuration. The performance of the PV panels varies based on the module type. There's three primary types of PV modules that are on the market, and that's what we're seeing here today. So each type of PV module or PV panel is comprised of multiple cells. So manufacturers make solar cells or PV cells, and they put those solar cells together to make a PV module. So a PV module is comprised of multiple cells that we can see in these images here. There's three primary types of solar cells that are available in the market. What's called monocrystalline cells, polycrystalline cells, and then thin film cells. So the vast majority of the solar market, monocrystalline and polycrystalline, that makes up about 90% of the global supply of solar energy. So the majority of solar anywhere in the world is monocrystalline and polycrystalline. They're both very good products, and they can actually, in theory, monocrystalline is a little bit more efficient than polycrystalline if we look at efficiencies. But in practice, sometimes the difference is not actually even in monocrystalline or polycrystalline. It's in manufacturing types, in different ways that different manufacturers all over the world take those silicon-based solar cells and they manipulate them in different ways to try to get better efficiency. The majority of the world's solar, which is mono and polycrystalline, is going to live somewhere between about 15% efficient on the low end, and right now about 22% efficient on the high end for commercially viable products. Now we see technologies that are getting above 22% efficiency, but a lot of those are kind of still in testing and aren't quite as commercially available yet. So that's kind of the majority of the market, is about 15 to 22% efficiency. Which is great, actually. And then thin film is kind of the third type. Thin film comes in a few different cell chemistries that we see out there on the market. Some thin films have a pretty low efficiency, down in the 6 to 8% range, and some thin films are high efficiency, similar to the crystalline modules that are getting into the 16, 17 or so % range. So Thin film, like I said, is only about 10% of the global market. And so the monocrystalline and polycrystalline is what you're going to see for most of the applications that we see out there in the world. Now, we were talking about cells. Let's talk a little bit and look at the modules themselves. PV modules are wired together to create what we call a PV circuit. And so there's a number of different kind of physical attributes to a PV module or a PV panel. Most of them in the market have a glass front. So it's glass on the front, it's cells in the middle, and then it's going to have a back, what we call a back sheet, which is usually plastic. Sometimes it has what we call a double glass, where it might have a glass back sheet, but most of them have plastic on the back, glass on the front. The larger modules that are in the market are usually come with a pre-wired output conductor. So we see the wires that come off from this image. So we have what we call a junction box, and the DC electricity comes out of that junction box, comes out through these wires. And most of these systems now and these modules have connectors, and the connectors make it easier and safer for us to create PV output circuits to run to whatever equipment we're going to operate. So the connectors that we see on solar modules are designed to be touch safe and waterproof. And so if they're put together correctly, then we can have a good electrical connection that's allowed to live outdoors for the majority of its life. Now, the other parts of the module itself, most of the modules have a frame, some sort of an aluminum frame around the sides, and we use that for mounting. So we take the aluminum frame and we bolt it to a mounting or a racking structure. The image we see here on the right is a ground mount structure where it's an elevated ground mounted solar array. We can see the aluminum frames. We can see where it's bolted through to the steel structure. We can see the wiring connections and those connectors to make up the PV circuits. And that's how we build up PV arrays of larger size, by interconnecting the wiring and by mounting them to some sort of a structure. There are a few panels out there that don't have frames. We call a frameless module. They have different clips that they grab onto glass, kind of like we put windows in and things like that. But this is the majority of the common solar panels that we see out there in the market today. Now, the other major component in any solar electric system is what we call the inverter. The inverter, as its basic, simple function, the inverter does DC to AC conversion. That's what an inverter does. We do DC to AC conversion because PV panels produce DC, similar to a battery type of system. And then we usually use AC in most of our electrical situations, whether that's our home, our business, industry, running motors, whatever it happens to be. So we really live in an AC world, and most of the devices we use are AC. So the inverter is a device to convert DC into AC. That's the simple term. Now, there are a ton of different inverters out there on the market, and different inverters out there are designed for different purposes. And so other than DC to AC conversion, these inverters are capable of doing all sorts of other things for us. So it is a piece of power electronics that converts energy, but it also is able to do things like utility grid synchronizing. So if we buy the right inverter type, we can have this inverter automatically synchronized to a utility grid, matching up its voltage, its frequencies, its waveforms, and able to push that solar power into an AC electrical system and match it at whatever type of electrical system we have. And so that's where we're going to use an inverter, is to basically convert energy and then synchronize it if we're connecting to the utility grid. Now, there are a lot of different inverters on the market that are designed for different applications. So we need to know what type of inverter we need, so we select the right inverter for the application. But that's the basic concept, is DC to AC conversion. Now, when we look at taking a step further into this utility synchronizing type of inverter, these types of inverters are very common in the market, and they're designed to be connected to the utility grid. And they can be built on different scales: utility scale, commercial applications, and residential applications. These particular utility synchronizing inverters are designed to operate without a battery. It's not a backup power system for these types of inverters. So an inverter like this requires a stable utility connection in order to operate. We'll talk a little bit more about that in another lesson, but these are designed for when we have an electrical grid that's stable, that doesn't go on and off a lot, doesn't fluctuate. And these systems are the way that we can have, at the end of the day, the lowest cost of solar energy delivered into an electrical grid. Now, when you see on the left here, the utility inverters, we have a couple different types and sizes. The ones on the top we call a string inverter. Those are big units that, in this case, that's for a power plant system. And a bunch of those inverters are all put together to work as one kind of big electrical generator. Down below we call a central inverter, a big concrete pad mounted single unit, also for utility scale power plants. When we get into mid-sizes for buildings and factories and commercial applications, we'll get some mid-size and scale inverters that are specialized for things like apartment buildings and other sorts of facilities. So the size of the inverter is going to be based on the application, of course. And then for residential, we have a couple different types of inverters we see for residential use. On the photo in the top right, those small black boxes that are mounted to that structure, those are what we call a microinverter. Microinverter is a small utility synchronizing inverter that's designed for one inverter for one solar module. And so that's a way to have small to mid-sized systems on homes. The photo in the bottom right corner is kind of a mid-sized string inverter. So we could take maybe a 5 kilowatt solar array, connect it to our utility system at our home, and push that energy into our electrical grid. So we see inverters that are utility synchronizing in a number of different shapes and sizes that are all designed for different applications. Now, if we start to get into battery-based systems, we have different inverters that are intended to be battery-based at all times. These inverters connect with batteries and solar arrays to then basically not only convert DC to AC, but also can utilize the battery bank for backup power. So these types of battery-based inverters are designed for either off-grid, standalone type systems, or backup power type systems like uninterruptible power supplies, UPS systems, things where if the utility fails, we run on backup power from solar and batteries. The utility comes back and we resynchronize. So battery-based inverters have a very specific application, but they're different equipment. We can also use some of these battery inverters for things like microgrids as well. Now, we talked about inverters and solar modules. Let's talk a second about batteries themselves. So if we want to store energy because we have a utility that comes on and off and we want to have backup power at night, or we live in a remote place and we have a standalone system, there's a number of different batteries that we can use as our means to store electrical energy. We're seeing 3 different kind of standard types here. One we call a sealed lead acid. It's our basic lead acid technology. It's been around for a long time, but these sealed batteries are designed for very specific deep cycling applications. And so when we look at all of these batteries, these are not a car battery. Even though it's the same technology from a chemistry standpoint, it's not the same type of battery we use to start our car. These batteries are all called deep cycle batteries. They're meant to act different than a car battery. So we want to make sure whenever we're buying batteries for solar applications, we're not buying automotive and car batteries. So these are bigger, more industrial and more purpose-built for cycling like we do in a solar system. So a sealed battery means that it doesn't have anything to do internal maintenance on. There's no checking of liquids. So it's all sealed up. We need to do maintenance on the outside to make sure we don't have corrosion, but everything's sealed into that battery itself. And that's why we can see these batteries are mounted on their side with the terminals facing out. In the middle image, we see flooded lead acid. Flooded lead acid is more of the older traditional style of batteries that's been out there for a long time that we've all seen. And these are the type of batteries that have caps that we need to open up and check the water and do internal maintenance by making sure we water the batteries and keeping them all happy throughout their life. Now, even though flooded lead acid is an older technology, it also has a much lower cost compared to some other technologies on the market. So there's still a very viable product depending on the application and the cost and our cycling. So we still see a lot of flooded lead acid out there in the world, especially in solar applications. Lithium ion is something that we've become, common with over the years as the advent of, more mobile technologies, electric vehicle systems have really brought on the lithium ion, movement in a way. And so we're able to utilize lithium ion batteries for solar projects as well. The cost continues to come down. Lithium had been very expensive, and the cost is continuing to decline for lithium, so it's becoming more and more affordable in different applications every year. Lithium battery banks often look more like a computer rack or a computer IT cabinet or something like that, because we do have a little bit more advanced controls that go with lithium batteries. So we'll see them usually fitted with some communication wiring and things that they have internal cell communication throughout the lithium ion battery banks. Now, anytime we use a battery in a system, batteries need to be managed in a different way. And so if I use a battery, then I'm also going to use what's called a charge controller. So charge controllers are designed to manage the PV array and control the battery charging. So they're going to be the interface between the solar and the battery. So they do a number of things with the PV array as far as making sure we get the most production out of the PV panels. But then they also manage the battery bank to make sure we don't overcharge the battery. So if the battery becomes full, the job of the charge controller is to turn the solar off and let the battery come down, and then it can reconnect the solar. It can also ramp up and down. And so maybe as the battery gets close to full, the charge controller goes to 75% or 50% output from the PV panel, and it'll regulate the charging of the battery that way. So anytime there's a battery in the system, we need some sort of a charge controller, or often called a charge regulator, that's built into the electrical system. Now, other main components that we have that are really kind of our basic electrical components, things like disconnects or isolators. So disconnects and isolators allow separation of electrical equipment and systems. And so we can see these in different places. The reason we have disconnects and isolators throughout our system is to make sure that we have the ability to do maintenance, or if we have any emergencies where we need to shut down or isolate something. So in the image on the left, we see a PV disconnect. And that PV DC disconnect, the one on the bottom of that inverter, it's called a rotary switch, and you turn that switch and you can turn the DC side of the system off. Those little plug connectors on the bottom of that also can serve as an isolator. If we turn the switch off, we can unplug those and isolate the solar array from the inverter itself. On the AC side, we have sometimes different types of inverter AC disconnects. So that's just what we call a knife blade or a normal blade or handle type disconnect switch that we might use for any sort of electrical device or motor load out there. And so sometimes that's used as an interface between the inverters and the AC electrical supply or the utility grid. And then also things like circuit breakers. In this case, if we have a battery bank, we want to be able to isolate the battery bank from the electrical system to do maintenance and testing or troubleshooting and things like that. And so sometimes disconnects are just switches, and sometimes they are things like this, which is also a switch and a circuit breaker. So that leads us into talking circuit breakers. Well, circuit breaker, like I said, can act like a switch because it's a handle and it can be turned off and turned on. But circuit breakers are there to protect each circuit from excess current, which means if we have too many amps or too much current in a circuit, then the circuit breaker is going to open that circuit, stop that flow of electricity in order to protect either our wires or our equipment throughout the system. So circuit breakers protect our equipment to make sure we don't send too many amps overheat something and cause a problem like a fire or any of those sorts of things. So we see circuit breakers all over in our electrical world that run our homes and all of our appliances and things like that. We also use circuit breakers in PV systems to either connect to batteries or inverters. The one on the right we see as an inverter output PV circuit breaker. So that's an AC side, three-phase output circuit breaker that's connecting an inverter to an electrical service panel. Sometimes we can end up with fuses in the system as well, depending on the application and the equipment. So fuses come in different places, and what fuses are there for is to protect each circuit from excess current, the same way the circuit breaker did that we just discussed. The difference is a circuit breaker protects the circuit by tripping the switch in the off position. The fuse opens internally, and then that fuse has to be replaced. So that's a physical manual replacement if we blow a fuse. So a fuse is there that's meant for a one-time use. If there's too many amps, the fuse will open, and then a technician needs to go in and see what happened, why did the fuse blow, and then replace it with the properly sized fuse. So see in the photo on the left, we have an AC disconnect with AC fuses in there. Sometimes fuses are hidden. So if you see in the middle photo, we have small fuses that are up inside those, what we call a tip-out fuse holder. Same thing on the right on this fused PV combiner. Each of those are PV source circuits that are combining together to make one larger solar array connection to an inverter. And we protect each of those circuits with a fuse to make sure that we never do any damage and we have a safe electrical system. Now, other than generating electricity, we also need to measure electricity. So we see different types of electrical meters that come in different shapes and sizes. A lot of times what we're going to look to measure is production of energy, like from our solar array, and consumption of energy, like in our homes or businesses. And so sometimes we'll have 2 meters on our system, one to measure the consumption of the building, one to measure the production, and those can be located in various locations throughout the electrical system depending on the physical layout. So that allows the consumers or the utilities, or sometimes we can set these up as a remote monitoring system so we can read them remotely and know what's happening in our electrical system. And of course, last but not least, the reason we're creating all of these components to build a solar electrical system is so we can operate our loads. Our household appliances that correspond to most of the electrical load usage. So these are the big normal things when we're looking at a residential or household load list. Things like lighting and charging phones and batteries and TVs, washing, refrigeration, air conditioning, all of our normal household usage. We need to understand what these loads are so we can design systems that best meet the needs of our client. And so we need to understand the loads anytime we dive into starting to do design. We need to know what we're designing for and what sort of electrical consumption we have before we begin figuring out what sort of solar system is going to best meet my needs.